Hello all. Today we are going to discuss about relation between GCD and LCM. And it's not only about relation. When we have multiple variables in GCD and LCM, how to operate on that and how to simplify. And we are also going to learn distributive law of GCD over LCM and vice versa. So first, we are going to learn with the very elementary assumption, that is GCD of A by D, comma B by D, where D is a common divisor of A and B, would be equal to GCD of A comma B, the whole divided by D. This is one. Second, we will also assume that GCD of A comma B equal AB upon LCM of A comma B. So you can also ask a question about the truth of this statement. I will leave that to you as a homework, but we will work with some multivariables in order to extend this. For example, if you consider GCD of 3 variables, what does that mean? It is the largest number D that divides A, B and C. Simple. And LCM, it is the smallest number which is divisible by A, B and C. So that's how we define for multivariables. When it is 4 variables, appropriately the condition shall change. Okay, there are other ways of expressing it, but that might not be obvious. So I want to make it obvious today. GCD of A comma GCD of B comma C. What do you think about this expression? Is it the same as the previous expression? Well, we first need to understand what this signifies together when considered with this. Well, this is the largest number that divides both B and C, and when you take the GCD of that with A, it is the number, say L, that divides A, B and C, because it is the divisor of divisors of B and C and also divisor of A. And why is it the largest such? Because any divisor of B and C should be also a divisor of its greatest common divisor. And hence, that's the largest divisor dividing all 3 variables. Now, this is not the only way to express. You can also write this as GCD of A comma B, comma GCD of A comma C. Since this number L divides all A, B and C, it must divide the GCD D as well. Not only that, we will now prove that GCD divides this. The reason is that GCD divides GCD of A comma B, that is the number D here divides GCD of A comma B, and it also divides GCD of A comma C, and hence it divides the GCD of these 2 numbers. So therefore, we arrive at the conclusion D divides L. Now L divides D and D divides L shall imply together L equals D. So this means the same expression GCD of A comma B comma C can be denoted in these 2 forms. Now a similar argument can be taken for LCM. So if you assume LCM of ABC to be D, then that value will also be equal to LCM of A comma LCM of B comma C, and that is also equal to LCM of A comma B and then LCM of A comma C. And the proof of all these 3 being equal follows a similar or analogous proof as we did for GCD. So you can take LCM of some 2 numbers inside LCM without altering its value. But what is more interesting and takes forward for further analysis is the combination of GCD and LCM. When you blend them together, how do they interact? And that's where we come to the distributive law of GCD over LCM. First thing, we will learn the distributive law of LCM over GCD. You also have an equivalent one, distributive law of GCD over LCM, but we will learn one by one. So what does this state? It says that LCM of A comma GCD of B comma C equals GCD of LCM of A comma B comma LCM of A comma C. So this is how they distribute. The equation is quite fascinating because this helps us to evolve to multivariables. First, let's quickly see what could be the proof of it. So first we start with the LHS, LCM of A comma GCD of B comma C. Okay, now this is equal to the product of A and the GCD of B comma C. That is the product of the two variables divided by GCD of these two variables. But just now we saw GCD of A comma GCD of the other two variables is equivalent to writing the GCD of all three variables. Okay, by the very first property, we can express this as A times GCD of B upon GCD A comma B comma C by GCD of A comma B comma C. And clearly GCD of A, B, C divides both B and C. So that's why it's meaningful to take it inside. Alright. Now I'm going to divide these values by some number that is co-prime to the other so that it will not affect the GCD. Notice that we could consider two numbers, GCD of A comma B and C, and then divide them by GCD of these two numbers. But what is the GCD of these two numbers? It is the GCD of ABC. And upon this division, the two resulting numbers shall be co-prime. These two values shall be co-prime because you have divided by their greatest common divisor. When you factor out their greatest common divisor, you are left with two co-prime numbers. And hence, since the GCD of these two equals 1, I can divide this number to the LHS, I can divide this number with the left side expression as it is co-prime to C by GCD of A comma B comma C. Not only that, by similar argument, I get the GCD of A comma C by GCD ABC is co-prime with B by GCD of ABC. And hence, I can divide, and thus I can divide this number with this number as it is co-prime to the left side expression. You see, this and this are the same. So I can divide this number with this number as it is co-prime. So whenever you are dividing or suppressing a factor that is co-prime to the other factor, you are not anyways affecting the greatest common divisor of those two numbers, right? Greatest common divisor should divide both. When you suppress a factor that's not here, we are well. Alright, so we get A times GCD of B by, so when you divide this number, you get B by GCD ABC divided by GCD of A comma B by GCD ABC. These two would get cancelled and you are left with B by GCD of A comma B, and that's what I'm writing here. And then this will be also similarly changed as you are going to divide by this factor GCD of A comma B by ABC. So that will give you C by GCD of A comma C. Now let's take A inside. You get GCD of AB by GCD of A comma B. This is by the very first rule we saw that taking inside a common factor to both the terms or taking out or filtering common factor from both the terms is allowed in GCD, comma AC by GCD of A comma B. And this is nothing but the expression of LCM of AB and AC. Hence, we arrive at the required expression. LCM of, this one will be GCD of AC. So you get LCM of AC. And another way to write this is LCM of A comma GCD of B comma C equal GCD of these two, which is the product of them divided by the LCM of those two terms. And LCM of 2 LCM, as we saw earlier, it is going to be the LCM of all three terms. And this is exactly our distributive law. We will incorporate in our further analysis, or you can do it for your problem solving. So further, if I move forward, I get A times GCD of B comma C divided by GCD of these two, which is, as we saw, GCD of A, B and C. Now that is LCM of A comma B, LCM of A comma C by LCM of ABC. Since all these terms are in LCM, you can also convert this to LCM. You get BC by LCM of B comma C, and after moving the terms around, you get the following expression. GCD of ABC equal ABC by LCM of A comma B times LCM of B comma C times LCM of C comma A, and in the numerator you have the LCM of all three values getting multiplied. So this is the relation between GCD and LCM when it comes to three variables, and we use the distributive law to derive it. Further, you can define a corollary based on this. What's that? Well, we saw the distributive law works when you have single variable and then a GCD of two terms. But it's not only restricted to that scenario. Suppose you have multiple variables like A, B, C up to, let's say, X, and then you have GCD of two numbers Y and Z. So how to find this? I can write this as LCM of those variables A, B up to X, comma GCD of Y, Z. Then I can apply the distributive law and then get that it is GCD of LCM of this and this, that is LCM of A comma B to X comma Y, and then LCM of A to X comma Z. I'm just applying the distributive law by considering this entire thing as a single term, because LCM of this would be a value. Now it is obvious to note that this is GCD of LCM of A, B to X comma Y, and then LCM of A, B to X comma Z. So now a similar distributive law is what happens for multivariables. You see, we started off with LCM of A to X and then had GCD of Y comma Z. So sort of these all variables distributes nicely inside. This is like a corollary of what we derived as distributive law. Alright, now you can apply this corollary to derive the GCD of 4 variables in terms of the LCM of a certain number of variables. How? Well, GCD of 4 variables is nothing but GCD of A, B, GCD of C, D. And thus we have now converted it into a single term. So this should be your logic. Whenever you are trying to generalize, try to hinge upon the inductive idea, where you use the previous result to find the new result. And therefore, this can be simplified by A, B times GCD of C, D divided by LCM of A, B, LCM of A, GCD of C, D, and then LCM of B, GCD of C, D, and then LCM of A, B, GCD of C, D. And now you can just simplify these 3 expressions using the distributive law we studied. Whatever be the number of variables, I know that LCM nicely distributes over the elements inside the GCD. So this would be nothing but GCD of A, this would be like GCD of LCM of A, B, C, LCM of A, B, D. So likewise, you can simplify that and then express everything in LCM, and you will be amazed to see that the expression is ABCD by the product of LCMs taken 2 at a time. I'm just writing A, B, but you need to take symmetric product. And then product of LCMs of variables taken 3 at a time, again symmetric product, by the LCM of ABCD. And now we observe a pattern. So whenever you write LCM of one more variable, you alternate between the numerator and denominator of the fractions. So using this and by strong induction, you can actually use weak induction to prove that GCD of n number of variables, A1, A2 up to An, is nothing but product of all the AIs divided by product of LCM of 2 variables where the variable pairs are unordered, and in the numerator product of LCM of 3 variables AI, AJ, AK, and once again they are unordered, divided by product of LCM of 4 variable AI, AJ, AK and AM, and the product just goes on where all products are unordered tuples of these variables. So this is quite interesting. We just started off with one distributive law and we were able to derive up to here just using one property, that GCD of n variables can be expressed as GCD of n-1 variables by considering GCD of the last 2 terms instead of individual terms. So using this and weak induction, you would be able to prove this. Now let's discuss the distributive law of GCD over LCM. So that is GCD of A, LCM of B, C equal to LCM of GCD of A, B, GCD of A, C. So it is just the same as before, but LCM and GCD are just swapped. I will give us a homework for you to prove this and also derive the properties of LCM of n variables in terms of GCD of some number of variables. Put out in the comments your ideas and your strategies and your thought process. We will discuss in the next video. Thank you everyone. Bye.